So, hello everyone. Welcome to the seminar series of INDUS. And today we have with us Chitradeep. So Chitradeep is a fourth-year PhD student at the Center of Excellence in Space Sciences, India, also known as CESI, a part of ISER Kolkata. And he is also an active member and one of the working group coordinators of INDUS. And his research interests primarily revolves around numerical simulations and observation of solar interior and surface magnetic fields, extreme solar activity phases, and space weather. So today he will be giving a talk on the sun and Odyssey through moments, millennia, and beyond. So Chitradeep, I request you to go ahead and start, please.
Thank you, Agodi, for the introduction, and thanks to everyone who have joined. I'm very glad to have you on board in this journey with me, where I shall rather tell a story of our nearest star, which is dynamic in nature, whose output varies in time, and how does it encompass a wide range of timescales, starting from, let's say, seconds to minutes to hours, two decadal timescale, two millennium and multi-millennium timescales. My primary focus will be on the longer timescales. That means the decadal and century and multi-millennial timescales in this talk. To start with, okay, fine. So what you're looking at is a snap of the sun uh, taken by Solar Dynamics Observatory, AIA instrument in, I guess, 94 angstrom, where you see the flaring regions during solar maximum phase, where you see a magnetically busy sun, where there are so many active regions. You see magnetic structures, not much clearly, but these are there. And on the other hand, right side, you see a quiescent kind of sun during solar minimum. And this transition from maximum to minimum, as we all know, it keeps on happening with a characteristic timescale of roughly around 11 years or so, which is known as the sunspot cycle or 11-year solar cycle. How does it look like in white light? You see many sunspots during solar maximum phase, or let's say a phase between solar minimum and solar maximum. On the other hand, you see relatively quiet or almost spotless sun for some days or months during solar minimum. It is basically the activity is the magnetic activity I'm talking about. But what about if you don't see any magnetic sunspot for, let's say, longer time, which means several years, that's it, or say several decades. Actually, these kind of things have happened in the past, and this is a special activity phase of sun and sun like other stars, which is known as grand minimum. For sun, it is called solar grand minimum, and I'll talk about that. Let's keep rolling into the past. You're looking at a picture uh, drawn by a medieval Dutch artist, Hendrik Everkamp, who drew this picture during 1608 AD. It's a landscape, frozen landscape of Netherlands. And this freezing of lake for a sustained amount of time was very unusual during those period in Europe, and it is essentially known as the Little Ice Age, and it had lived profound influence on people's lives, as you can see. There are so many people, they are doing their daily chores. Some of the people, they are skating on the frozen lake. In fact, there has been record that the River Thames in London, it was frozen for many years during that time. It's called Little Ice Age. We are magnetically connected to the sun. So if there is something happening on the earth, this might have some influence from the sun as well. And this is a picture taken from a recent review that we have written from this group. So what this connection tells about? how was the sun doing during this time? Let's have a look about on that thing. So there are astronomers who had taken into account of this sun going into a relatively quiescent phases, where you see very few to very low number of sunspots during this sustained amount of time, many decades, 70 years or so, starting from 1645 to 1715. And this is famously known as the Maunder minimum. Gustav Sporer was the first one who noticed it, and then research was carried on by Annie Maunder and Edward Maunder at the Royal Greenwich Observatory, who studied these solar grand minimum kind of phases in details. Despite the fact that there is a temporal overlapping between this little ice age and solar grand minimum or Maunder minimum to be specific, you cannot really say whether solar grand minimum really caused this little ice age, because a mere correlation does not imply causation. There are many theories, there are some controversies that revolves around that. Some people believe that volcanic eruptions were the main cause of driving this little ice age kind of climatic condition on the earth. But let's not talk about those controversy. Let's focus on solar grand minimum phases. And for that, this only 400 years of direct observation we have with us. And that's not sufficient, of course, to conclude anything on the nature or the dynamics of these solar grand minimum phases. But there is a way out, because nature preserves the activity record of the sun for million of years, of course, more than centuries and more than 1 millennium. You have cosmogenic isotopes, which has very long time scale of half-life. You have beryllium 10, carbon 14. Carbon 14, for that matter, has a half-life of around 500 years. For beryllium 10, it has a half-life of around 5,000 to 6,000 years. And what happens, the solar activity actually regulates the abundance of these cosmogenic isotopes through the flow of cosmic particles that emerge from the supernova explosions in other galaxies. So there is a direct anti-correlation between the solar activity and the abundance of these cosmogenic radionuclides. When the solar activity is high, the abundance of these isotopes are low, and when the solar activity is low, the abundance of these cosmogenic isotopes is high. And the beautiful thing is that these isotopes are deposited in the ice cores, deep in the polar ice core and tree rings. So all these activity records, those are being preserved for millions of years. And there has been active efforts in looking at those records and recovering how was the sun doing for, let's say, past million of years. And what you see here is a plot of solar activity record calibrated to the modern day SEALS observation, sunspot number observation. It essentially shows there have been several instances of grand minimum, sustained amount of time, when you barely see any sunspot emerging on the solar surface. And they're historically known as Wood, Wolf, Sporer, Maunder, and Dalton minimum. This is confined to this starting from 971 BC to 2000, 971 AD to 2000 AD, basically this century. An important question is, in fact, this is taken from Wikipedia. The question asks, what caused the Maunder minimum and other grand minimum? And how does solar cycle recover from a minimum state? And to answer that, only observation are not sufficient, because when you observe when you look at the sun, you essentially look at the surface. But the real answer lies within the interior of the sun. And that's why, and that's how numerical simulation of the solar interior becomes important. There are so many assumptions, but the crux is that you assume the plasma flow in the solar interior, they basically generates and sustain the magnetic nature of the sun in a recyclic manner. And this is called a dynamo mechanism. On the left panel, you see a kind of dipolar structure of the sun, which is the case during solar minimum, and you get kind of multipolar structure, which is shown in the rightmost panel with a potential field source surface extrapolation based on the surface map of the sun, where you see so many simulated active regions on the sun's surface. So from this shift from dipolar to multipolar structure and back to dipolar structure, this is essentially the magnetic cycle that sustains and that generates and sustains this magnetic behavior of the sun. And the middle, you see in the right meridional plane, there is a flow kind of structure. This is one of the weakest flows, most weak flow in the solar interior. This is known as meridional circulation. On top of that, you have differential rotation. As we all know, sun rotates differentially, which is different than solid body rotation. Sun's equatorial region rotates faster and polar region rotates slower because of angular momentum transfer from polar region to equatorial region and vice versa. And what happens, this global circulation of meridional flows and this differential rotation and also superconnular diffusion, all of these work in tandem to generate and dissipate the magnetic field. If you start from dipolar structure as it is shown in the leftmost panel, this differential rotation causes these to wind up along the axis, and this is called omega effect. And in a similar way, this winded up structure, they unwind and goes back to the dipolar structure, which is known as alpha effect, alpha mechanism, which was proposed by Parker during 1955 in his phenomenal paper. In this schematic diagram, you see the sun starting from a relative dipolar structure and this differential rotation and the meridional circulation and superconnular diffusion. They cause these field lines to be dragged along the sun's motion along the phi direction, azimuthal direction. And on the other hand, this circuit continues and it goes back to again into a dipolar structure starting from a multipolar structure, which is basically governed, which was explained by Parker through some helicity mechanism, unwinding of a bow interruption of the loops to the surface and their twisting and stretching and their poleward migration. And then again, this cycle continues. I'll not focus much on the theory behind and the numerics behind this solar dynamo mechanism. Let's have a look. As I pointed out, this solar cycle is basically sustained by the weakening of the dipolar structure and the strengthening of the multipolar structure, let's say that's the toroidal field, and again weakening of the multipolar structure and strengthening of the dipolar structure. Basically, this dipolar structure, the energy stored in these dipoles, they basically feeds in, and you see sunspots being emerged on the surface. And if you focus on the middle panel, you essentially you are looking at the evolution of axial dipole moment of the sun for the past couple of decades, and in the lower panel, the corresponding evolution of the sunspot number. Recently, this has been explored that the weakening rate of sun's dipole is causally connected to the rate of surge or emergence of number of sunspots. The faster the dipole moment decays, the faster the sunspot cycle rises. I'll not talk much about that because I hope we will have the lead author sometime in this forum to talk in more detail about these results. And what is beautiful about this study is that you can more precisely predict when are you going to achieve or going to reach another solar cycle maximum. So for that, you should check this newly published article, which came online only day before yesterday, and it has already is all over the news, as you can see. So let's go back to the dynamo mechanism. You can always simplify being a modeler anything complex that is happening out there in the nature. So starting from a 3D, which I showed you earlier as a part of underdeveloped under development, which is currently I'm involved in developing at SESI. We can always simplify these models, and we can assume an axis symmetry, which means as you rotate around the sun in this azimuthal direction, you see no particular changes. Essentially, in mathematical term, del phi equals 0. Once you incorporate this assumption, your life becomes easier, and you end up with a two-dimensional, rather 2.5 dimensional equation, where essentially in the first equation you see an evolution of sun's toroidal magnetic field, which is along the phi axis, and in the second equation you see the evolution of sun's colloidal magnetic field. A is the vector potential, which gives rise to colloidal component of the sun's global magnetic polar field. And this del B del T and del A del T, their generation and their dissipation, they basically depend on large scale flows, which is shown by VP term here. And S is basically r sine theta, a geometric term. And there is a diffusion term, which is eta T, that depends on space. Uh, it doesn't vary over time. And also this flow profile, it is kept fixed in time. That's why these kind of models are called kinematic models. And such kind of kinematic models have shown very good results, and they corroborate with whatever you observe on the sun's surface, at least. And if you talk about full MHD simulations, there are many drawbacks, and there are still many scope to improve those simulations, because still now we haven't achieved the solar-like differential rotation being generated self-consistently out of full MHD simulation. That's how we rely on kinematic dynamo simulation and reduced dimension. To model these extreme magnetic activities, we incorporate stochastic forcing in the model. And essentially, these forcings are encrypted in those source terms, alpha B here. And this alpha B term is called the generating term or the colloidal source term, which couples this B with this B. And you keep on solving this coupled system of equation and generate a time series of how the large scale magnetic field of the sun is evolving in time. Also, we incorporate this stochastic forcing independently in both the hemisphere, because for obvious reason, these hemispheres are not much strongly coupled. There is coupling, but for sake of simplicity, we just incorporate independent forcing for the two hemispheres. Now, how does the result look? Indeed, we can simulate such kind of extreme activity phase, starting from grand minimum to grand maximum. What you are looking at the right, at the left panel is the time series of 10,000 years of simulation of sunspot number, where you see many phases where you see barely any number, any sunspot on the sun's surface. Let's say, for that matter, these phases. And if I just do some statistics, this distribution of duration of these grand minimum phases looks like what is there on the right plot. It ranges from 40 years to 20 years. And we found that nearly 22.7% of the total simulation time it spent, the star spent in a quiescent phase, which is kind of similar to what has been observed by Usoskin et al., which tells that nearly 25% of the time Sun was in a quiescent state for the last 11,000 years. This is kind of a sanity check of our simulation. Not only one set of simulation, we have done multiple set of simulation, and these statistics hold. We could get nearly 22 grand minimum episodes, while in the observation it is 27, and 2.4% of all the solar cycles, basically 900 solar cycles, they were in a grand minimum state. What is interesting is that you see very interesting dynamics in the polar region of the sun. On the top panel, what you see is the evolution of Sun's magnetic map on the surface. These are sunspot emergence proxies. As you know, the solar cycle progresses, the location of emergence moves towards equator because of meridional circulation and circulation in the toroidal field belt in the deep interior. And the flux stored in these sunspots, they migrate towards pole because of, again, meridional circulation. This is called flux transport process on the solar surface. You can also simulate that with the SFT model, surface flux transport model, which only takes account of the radial field evolution on the sun's surface, unlike dynamo, which takes care of all the internal fields as well as the surface fields. We define this grand minimum when you see no emergence of sunspot in our simulation, and you see kind of synchronicity in the occurrence of grand minimum in this 100 years of snippet, starting from 0 to 100 from the 10,000 years of simulation. Along with that, you see a gradual weakening of the polar field as it enters into the grand minimum phase. Gradual weakening is there, and then the reversal stop. This is kind of an robust case for almost all of the grand minimum phases. Here as well, you see kind of halt in the polarity reversal. Before that, there is a gradual decay, and then again the polar field builds up, and again you see reversal. After the reversal is recovered, you see the regular sunspot cycles again on the solar surface. But what happens in the solar interior? In the solar interior, this is the magnetic map evolution at around 0.72 solar radius around the Takook line, where essentially it is believed that this magnetic field is generated due to differential rotation. You see, although weak, this sunspot cycle, this magnetic cycle keeps on reversing, and kind of ceaseless cycle is there in the interior. From observation, you see, just like as if the sun is taking a nap, it's not magnetically active anymore, it's quiescent. But through simulation, you can understand that something interesting is still happening there in the solar interior. That's why I call it the sun's slumber is not so deep as it goes to sleep. When you're dealing with time series, it is obvious to analyze this time series with spectral method. But before that, let's have a look on how the flux output of the sun during these phases evolve over time. On the top panel, you see flux in the northern hemisphere. In the bottom, you see the flux in the southern hemisphere. In blue, the evolution of polar flux. In red, you see the evolution of toroidal flux. The interesting thing, another interesting thing is that you see kind of fluctuations in the nature in the polar flux during this grand minimum, and this holds true for all these grand minimum phases. Are these merely fluctuations because we have a stochastic forcing in our model? This is not. This is kind of a valid argument that these are random fluctuations. But the answer will be clear once you do spectral studies on this time series. And let's do that. On the left panel, the results are for northern hemisphere. On the right panel, the results are for southern hemisphere. In pink color, you see the dynamics during solar grand minima. Actually, this is a result which encapsulates all those grand minimum phases, bit by bit, chunk by chunk. And in the black, you see the power stored in various frequency or let's say periodicity channels during regular activity phase. What is 29 meter per second? 29 meter per second is the peak flow speed of meridional circulation during these simulations, which is a bit higher for sun-like star. Typically, this meridional speed has been measured to be around 10 meter per second. But to sustain the model due to numerical reasons, we have to set this value of meridional circulation to a higher value, just so that we set the star in a supercritical regime and you see regular cycles. Uh, Interesting thing is you see a reduction in the power stored in the 11-year solar cycle during the grand minimum. On the other hand, you see the redistribution of power in the lower periodicity channels. This is 5 years, 6, 7, 8, 9, 10, 11. And this is kind of same for the other hemisphere as well. Reduction in the power stored, Fourier power stored in the 11-year solar cycle, and redistribution of the power in lower and higher frequencies. This is the simulation we get from the simulation. You also see enhanced 22-year periodicity here as well. Now, what does this 5-year or let's say 5 to 6 year cyclicity talks about? This is a typical time scale which it takes to dredge up magnetic field from the solar interior up to the solar active latitudes. 5 years it takes if you neglect the buoyant emergence of the sunspot, which is of roughly of time scale of a month, 27 to 30 days. So through meridional circulation, if you want to dredge up the magnetic field that is stored in the deep interior, it takes roughly around 5 to 6 years to, to transport this magnetic field from this point to a high latitude, let's say active latitude on the solar surface. Is there a causal relation between this meridional circulation time scale and whatever you see in the periodogram? Let's have a look. You vary this meridional circulation speed to 25 meter per second, and of course the whole dynamics shift to a higher periodicity regime. It takes longer time to dredge up the magnetic field from the deep interior and deposit it on the surface. On the other hand, if you enhance the speed of meridional circulation to 40 meter per second, the whole dynamics expedites and the whole spectrums shift into a lower periodicity regime, including the 11-year periodicity and the higher frequencies, the 5-year periodicity, and so. It kind of establishes a causal correlation that meridional circulation in the sun's interior and the mean field alpha effect in the solar convection zone can sustain weak solar cycles in the large-scale polar field amplitude, even during solar grand minimum, even if you don't see considerable number of sunspots, even if you don't see considerable activity on the solar surface, this magnetic transport of magnetic fields and their recycling processes, they keep on happening in the solar interior and in the polar region. This got attention of the media, and this was published nearly a year ago. And what is good about the result is that recently we had some observational support which corroborates this finding that these people, Yan et al., their recent study shows that during solar grand minimum, the mountain minimum, they reconstruct the activity based on auroral records, and they see indeed shortened solar cycle, as we pointed out, the redistribution of power into 5 or 6 years. They have shown 8 years cycle during mountain minimum. So that kind of lend an independent support to our simulated result. Talking about polar field, another valid question is when does the slumbering star awaken to its full glory? And we are currently analyzing this thing, and the preliminary answer is to quantify it. When the polar flux magnitude regains almost about 70 to 72% of the mean polar flux during regular activity phases, you see a reappearance and re-emergence of sunspots on the solar region. These are the results from very recent simulations, which are in preparation, again with Shanghita and my supervisor Dipyendu. And these two plots, these are for northern and southern hemisphere. I'll not talk much about the plot and the histogram. Let's reserve it for some other space-time. We are talking about longer time scales, decadal time scales, and century time scale, millennium time scale. Let's go beyond that, which is multimillennial time scale. This is the observation of a solar activity record, which is again recovered from cosmogenic isotope, and this is done by Usoskin's group. On top of this small scale modulations, weakening and strengthening of the sunspot group number, you see a super modulation kind of thing, which is shown in red, uh, which essentially shows that the amplitude and duration of the sunspot cycles, they also vary in time. And we call it super modulation. Any modulation which is beyond the 11-year time scale, we are referring it to here as super modulation. If we again go into the Fourier domain, you see beyond the decadal time scale multiple periodicities which are statistically significant. These are present there in the data. Now, there have been debate what is the origin of this supermodulation? Whether it is nonlinear quenching, because you cannot make the magnetic field grow beyond a certain limit. You should saturate it in a certain limit. That's why you have nonlinear quenching term in the simulation. That's why I call it the sun knows the limit when to stop and go back to solar minimum. And you also have stochastic forcing, as I already pointed out. So there is random forcing, which basically mimics the turbulent processes in the solar convection zone because of its extreme condition, very high Reynolds number of the order of 10 to the power 5 or 6. How to put it in the perspective of physics? The nonlinear quenching can be explained because the back reaction of sun's magnetic field on the flow. The flow is generating magnetic field, but because of Lorentz force, which is nonlinear in nature, J cross B term is there in your Navier-Stokes equation. In the reality, there is a back reaction which feeds back onto the velocity, and it tries to quench the flow locally, which manifests as a global phenomena, and it tries to reduce the overall generation of the magnetic field at the global scale. And also there is energy exchange between this dipolar and multipolar and quadrupolar structure, these parity modes, which is nonlinear. On the other hand, there are stochastic perturbations. You have helical turbulent buffeting of the rising flux tubes. on top of the Coriolis force, which imparts a mean tilt. Due to this turbulent buffeting, you have a randomness in the orientation of sunspots by poles on the solar surface. You have a contribution from the anomalous or rogue active region, which again impart kind of a random forcing on buildup of the solar polar fields. So all these things are there. Now, the question is whether sun is dominantly nonlinear or whether the sun is dominantly stochastically forced. And behind this supermodulation, what is important? Is it nonlinear quenching or stochastic perturbation? Uh, Here in this slide, I list a couple of references which basically summarizes these nonlinearities and stochastic perturbations which plays out in the sun, along with some of the relevant studies. I will not talk much about that, the technical details. Let's have a look here. What you're looking on the top hand panel are the periodogram analysis of power stored in various frequency channel, where you see a sharp peak around the 10 or 11-year periodicity, which is generated from a 2D model and with a second order of nonlinearity. On the right hand side, you see result from a reduced model where you don't simply consider any spatial dependence of the dynamic variable, but to encounter or to account for that simplification, you introduce some time delay, which essentially arises from the transport processes that it takes from one point to another point in the solar interior. So these stochastically forced time delay dynamo mechanism, these are, however, numerically more simple, but they can generate and explain how the sun behaves on a longer time scales. So on the top hand panel, you see the results with nonlinear forcing, but there is no stochastic fluctuation in the model, only nonlinear forcing is there. And surprisingly, you see no statistically significant peak, which is beyond this decadal time scale, uh, that is absolutely absent in your periodogram. What if you further increase the strength of nonlinearity to fourth order? This second and fourth order, this is a bit technical because I haven't shown their mathematical formulation. But let's say fourth order means we further increase the strength of nonlinearity, how nonlinear is the forcing back reaction of Lorentz force, okay? Even then, you see no significant change in the periodogram and you don't recover statistically significant modulation beyond this decadal timescale. This is a part of study which we had done with an undergrad Shuprabhu, and Dipendu, of course, was there, and we are currently preparing the results. And the takeaway message is that the stochastic fluctuation in the dynamo mechanism, it indeed plays the key role, and alone the nonlinear quenching cannot recover this supermodulation kind of behavior in the sun's magnetic activity output on longer time scales. To sum it up, I just leave you with this quote that there are still many mysteries lie there in the depth of this fiery ball. And I quote Carl Sagan that somewhere something incredible is waiting to be known. And this is the time to acknowledge to Indus for giving me this opportunity to present the work. I intentionally kept it non-technical and short. My thanks to all the working group members whose relentless efforts have made us going for almost half a year, and I believe we will be there for coming years and decades and many more solar cycles. My gratitude to whoever have joined, and my gratitude to my lab colleagues, whom you often find atop a tree or even mysterious places. my thanks to my collaborators, Priyansh, Suprabho, and Sanghita for being there during these studies. And that's all. I end up here. Thank you so much. I would be happy to take questions unless I have driven all of you to grand minimum. Thanks.
Thank you, Chitradeep, for this nice talk. I'm sure it was beneficial for all the people who are at various stages of their studies now. So the floor is now open for questions. If anyone has any questions, I request you to kindly raise their hands and then they can unmute themselves. Do we have any questions? Or you can put it in the chat and I can read it out. Okay, I'll give the participants some time to think if they have any questions. So in the meantime, I have one question, Chitradeep. So
Yeah.
when you do this simulation, so this question is coming from from the perspective of someone who does not work in this particular field. So how do you actually, so when you have these models, I'm assuming you have a spherical shell, right? That you consider like a thick shell, probably, where you
Yeah, essentially you
you
have a
perform this.
meridional cut.
Okay, so my
You
question
don't
is that,
consider the phi direction. You only have
okay,
r theta plane in the
okay,
2D model. In the 3D
so
model,
it's
of
kind of
course, you
an
have
annular.
yes, it is indeed kind of an annular shell.
Okay, so my question is that in that case, how do you actually constrain the physical properties in the inner part of the boundary where you don't really have any observations and you don't really know for sure like what may be going on there? What are your assumptions or what are your constraints in that particular boundary?
Right. The thumb's rule is that you consider the solid crust at the radiative zone as a perfect conductor.
Mm-hmm.
And then that's how you put your boundary condition at the inner radius of your numerical domain.
And as for velocities and energy transport, do you have any special treatment there?
Yeah, so as I already pointed out, you don't make the velocity profile evolve in time. Once you have prescribed it, it is kept fixed because it doesn't vary much over time, over longer time scales. So, and these velocities, they are of course constrained by helioseismological measurement, these meridional circulations, and your differential rotation. These of course these are constrained by observation on the surface and the helioseismological measurement. Yeah.
Okay. Okay. Thank you. So, do we have any questions in the chat? No. Let me quickly check again. No. So, okay, if there are no questions, then let's thank Chitradeep one more time, and that actually wraps up everything for today. And so it just remains for me to say that the meeting is now concluded, and thank you all for coming. We look forward to seeing you next time.
Thank you so much.